Essay 65, Part 2. It appears to have been Riemann who introduced the idea that the geometry of Euclid could be made into another kind of geometry which reduces to that of Euclid, but is at the same time more general. Riemann introduced the metric as a measure of the way in which his geometry differed from that of Euclid, whose metric using static Cartesian coordinates is a diagonal 3x3 unit matrix. In Riemann's geometry, the object known as the metric can become different from the unit diagonal, a typical mathematician's idea, one may think, devoid of all realism. These mathematical ideas have a habit, though, of becoming physics, which is the philosophy and description of nature, or natural philosophy. The greatest advances in physics are made by controlling the mathematics so that it does not become incomprehensible. If that happens, enlightenment is lost and we are back to dark matter again, or even worse, the Higgs boson. Riemann worked in the early part of the 19th century and worked only with the idea of the metric. In the 1860s, Christoffel introduced another way of making Euclid's geometry more general. Christoffel proceeded by developing the idea of the derivative using an object known very obscurely as the connection. Only mathematicians would think of such an utterly obscure label. In the Euclidean geometry, the derivative can be worked out with the everyday Cartesian coordinates, which define a static frame of reference. If, however, the cylindrical polar coordinates are used, the axes themselves move in time, and the derivatives are defined with extra terms as a consequence of the movement of the axes themselves. This example encapsulates the idea of the connection. The word comes from the fact that the frame of reference itself is no longer static. The state of the frame at one point in a given mathematical space is connected to the state of the frame at another point. The simplest example is rotation of the frame in two-dimensional space. The connection is then related to a rotation matrix. Almost always the rotation is thought to be the movement of a vector clockwise, for example, with static Cartesian axes. However, the same rotation can be described by keeping the vector constant and moving the axes counterclockwise. This can be described as rotational relativity. The rotation can be defined by a rotation matrix, and this matrix is an example of a connection matrix. The first piece of confusion I noticed in my purely historical researches in this subject is the misattribution to Riemann of the concept of connection, so it is known quite wrongly as the Riemann connection. It is the Christoffel connection. Riemann inferred only the metric, which is a symmetric tensor in contemporary language. Again, Riemann had no concept of tensor. This idea was introduced much later by mathematicians including Levi-Civita, Ricci and Bianchi. Riemann had no concept of vector, an idea introduced by Heaviside and Gibbs long after Riemann's time. Such confusion did not give me much confidence in the scholarship of those who claim to be experts in general relativity. The confusion about centrifugal force does not give me much confidence in school teachers who continue to befuddle their pupils with dogma, as if the teachers themselves are confused and are just doing a job to earn a salary, or even worse, drifting through a career. The crass misattribution of the Hooke law to Newton is very poor scholarship by those who claim to be seeking the truth about nature. These are examples of what I call fogma, or foggy dogma, coming from a laziness of mind, and in the worst case, catatonic boredom. They should have gone into another subject. In its full glory, the Christoffel connection is an object with 3 indices, usually written with 2 subscripts and 1 superscript. This is why it is known as the Christoffel connection. It looks like a hedgehog or porcupine into which no dog, short for dogmatist, would like to put its nose. The necessity for these 3 indices comes from the need to define a derivative in such a way that that derivative is a tensor known as the covariant derivative. With this definition, the connection takes on a life of its own. It is not a tensor, unlike the most general kind of coordinate transformation. Under the most general kind of coordinate transformation, it does not retain its mathematical structure. A nasty inhomogeneous term appears and the connection is not generally covariant. At this point, most dogmatists give up because they do not go further into the mathematics as it starts to get difficult. And the dogmatist becomes just that, a person who relies endlessly on the work of someone else and repeats someone else's ideas endlessly without understanding or ever checking them. The dogmatist is enveloped by fog and disappears from the sight of history. I suspect that the vast majority of experts are dogmatists. To go into mathematics is hard work without pay or promotion. To admit to having no knowledge of mathematics is much more honest. It is up to the physicist to explain all the obscurity in order that enlightenment may prevail. Otherwise, there is no purpose to what they are doing. They could get bigger salaries in other jobs, and the vast majority has no sufficient knowledge of mathematics. Some have no knowledge of knowledge itself. The word covariant is a horrible jargon. It means that the format of a covariant derivative is the same when that covariant derivative is transformed into another frame of reference. So what? One of my favourite enemies always used to fire off this question, or very common assault, without doing any work himself. The answer to those 2 little words is that covariance becomes a law of physics, a law of general relativity. It is one of the few things that have survived the scholarly criticism of the past decade by my colleagues at AIAS and myself. Mr. So What would fire off another round. Physics? So what? He is long vanished into total obscurity, the archetypical career man. The idea of the by now familiar vector appears to have been introduced into the latter part of the 19th century by a predecessor on the civil list in Britain, Oliver Heaviside, who used vectors to simplify the earlier Maxwell equations of electrodynamics. Maxwell himself did not use vectors, he used Hamilton's quaternions. Hamilton being another predecessor of mine on the civil list. Gibbs also played a leading role in the development of vectors. I always refer to the equations of electrodynamics as the Maxwell-Heaviside equations, abbreviated to MH. These can be written as 4 vector equations. 2 are homogeneous, 2 are inhomogeneous. The homogeneous equations deal with the electromagnetic field itself and are the Gauss law of magnetism and the Faraday law of induction. The 2 inhomogeneous equations deal with the interaction of the field with material matter, notably one electron. They are the Coulomb law and the Ampère-Maxwell law. The latter is named after Ampère and Maxwell because the latter modified the Ampère law with the Maxwell displacement current. These 4 laws were firmly based on experiments, and they first appeared as 4 laws in Heaviside's analysis. In Maxwell's earlier analysis, there are many equations, much more difficult to apply and to understand than those of Heaviside. In addition to the four laws, there are constitutive equations which introduce polarization and magnetization. For the purpose of this long essay, the key idea is that the MH equations are equations of special relativity. The modern era ideas of relativity originate in the MH equations. They are not equations of general relativity in the dogma or received opinion, to be as polite as possible, but in ECE theory they are correctly relativistic in general. A well-recognized triumph of ECE theory. End of part 2.